at this step, we need to design that data structure first. This data structure, our design goal, we want to support fast search operation. So that's our main concern, fast search operation. Given a key, so here, last time I talked about key value pairs. So the data organized in this data structure, key value pairs, key, search key. So with a given key, we can find the data stored in this value, key value pair. For the question, what is the form of the value? Because when we think about a value, we can consider the general case. The general case value, you can imagine, could be object. Programming object. So you know, programming object. Object-oriented programming. So we are talking about programming object. Right? Yeah. So you can store a block of data in one object. Structure data in one object. It could be a big object. It could be a big object. Right? It could be a big object. All right. So you can imagine key value pairs like that. This is the general case. Okay. Special case, the value is just one number. Special case. All right. Each data item is identified with a unique key. Okay? All right. Question: how to make your data search efficient? Here, to answer this question, you have a lot of freedom. You have a lot of freedom, right? No restriction. Okay. So, how to take advantage of your freedom to get the fastest search algorithm? All right. Data structure now given. You have freedom to choose, and you need to design some very efficient data structure. All right? Yeah. Keeping in mind, handle dynamic data efficiently. So you need to do data operations, insertion and deletion frequently. Okay? Yeah. Dynamic data. In the real world, it is very common. We need to deal with dynamic data. All right, here, in order to help you design the data structure here, I draw this chart to do comparison. Examine our known search algorithms. Here, rows, columns, algorithm properties. So that's just prepare for the design, data structure design. Linear search here, binary search here, right? And then there is another one, not very popular. Here, this column, I want to put another search algorithm. Nobody noticed that, but it's important we put here, index search. I'll explain this index search. It's rarely used because there is a very big drawback of The reason I put here, it can inspire us to design this new data structure. We get inspiration from this, data structure design. All right, data structure here. Yeah, this property when we look at data structure, array, index search, also array. Yeah. The meaning given an array, in order to search a value in the array, the index is used as the key. Is it fast to find the value? Given an array, the key is the index. Key is exactly the index. So you just use your key to find the value immediately. That's very fast. Yeah. So that one we call index search. Okay? Index-based search, key-based search also. Performance. Linear search, big O of n. Binary, big O of log n. Index search, big O of 1. Very fast. But why nobody use it? In the real world applications, nobody uses it. Because its drawback is huge. We will see it. Ordering. Unsorted, sorted, unsorted, unordered. Okay? Yeah. All right. Dynamic. Supporting dynamic data structure. Yes? Yes? All right. Costly. If you want to add a new element into an ordered array, you need to fix it. Fix it with big O of n. That's costly, right? Big O of n. That's costly. Yes, yeah, because you do not need to fix it, right? No order requirement needed. We don't need to fix it. All right. Efficient sorting. Efficient sorting. No. You need to apply sorting algorithm. That's not efficient. Okay? Here, yes. Because the array is already sorted. So you can get sorted data immediately. No. Okay? All right. Yeah, so that's all we have so far. Then for the new search algorithm, what do we want to have? New data structure. We need to design. Performance. We like to have big of one performance. Because it's possible here, right? You can see it's possible. So we try to get a similar performance. It could be a little slower. Big O of 1 could be a little slower. But you want to close to big O of 1. Unsorted, it's fine. You cannot ask for too much, right? Everything you ask for the best, it's impossible. It's impossible. Remember, when we studied divide and conquer, 3 steps. Divide step, conquer, combine. Conquer, we know recursion. Divide, combine, these 2 steps. You cannot ask both steps big O of 1. It's impossible. If one is big O of 1, the other you have to accept big O of n. Similar situation here. You can not ask for every property you get the best. It's impossible. You have to sacrifice somewhere. Okay? Trade-off thing. Here we sacrifice. We do not allow our data is ordered. We sacrifice here. Okay? Then we have to sacrifice a little bit somewhere. We feel, not that important. All right. Dynamic data, yes. We want to, do insertion, deletion, not that expensive. Not that expensive. Okay? Yeah. Better than big O of log n. Better than big O of n. Okay? That's what we feel okay. Not expensive. But later you will see this dynamic data management, this we have a big O of what? Average case, big O of 1. All right, efficient sorting, no, because these two connected, right? These two connected. If there is no ordered data, then you cannot get sorting efficiently. So that's the place we have to sacrifice. Right? Yeah. All right. We have our design goal. Next, the key part. How to get this. How to get big of 1. Average case efficiency. Okay? Yeah. All right. Get inspiration here, right? Index search. Let's start with index search. We find the problem, then we find the solution, fix it. After that, we get this new data structure easily. That's simple, right? Yeah. So let's start. Yeah. Look at the idea of index search. We want to generalize the idea of the index search. Okay. Simple, way simple idea. Nobody uses it. Usually you won't see, this search algorithm plays any meaningful role in the real world, the real world applications. Not practical. Here in our textbook, in the typical textbooks, it's also called direct addressing. Because the key, at the same time, it gives you the address information, so we call it direct addressing. Okay? Another name for this method, direct addressing. All right. The key property, we do a mapping between key and the index of the array. There is a map. Okay? So this mapping, just same number, that's the mapping. Okay? Key value, the same value as the index value. Trivial mapping. So we can call it trivial mapping. Okay? All right. The main problem, you can see this algorithm actually not useful. Real world applications, not useful. There is a big problem. All right. When the keys are long, because in the real world, many times the keys used for data search pretty much based on your business requirements. Okay? So you cannot put restrictions on it. The business requirements. For example, we use student number as the search key. Can you put any limitation on student number? No. The student number as is. Okay? You cannot change anything on the student number. Right? Social security number, another one that could be used as the key, search key. But you cannot put any limitation on social security number. You just use it as given, right? So those keys are long, are quite long. Right? Yeah. So in the real world, you need to deal with the long search key. But with long search key, this index search is useless. That's the problem. Useless. Yeah. Right. Because when you have a long search key, but the number of data items you need to manage, many times it's a small number. You may have small number of elements. Long search keys corresponding to relatively small number of elements. How can you do it efficiently? That's the problem. Because if you want to use the index search directly, you would waste a lot of memory space. Why is that? Yeah, let me use my next slide diagram to explain why we would waste too much space in this method. How to use space efficiently? So the issue is, in order to fix the problem, we need to find a way to use space efficiently under long keys. We cannot change the keys. Okay? So we should use the original keys. But we want to manage the space usage efficiently. All right, SSM or student number, long keys. All right. Here, let me explain why the space usage not efficient for index search. Long keys. Let's assume there are 40 students in the class. Okay? 40 students. It's a small number, 40. Right? Small number, 40. But if we use either student number or SSN as the search key, that's long key, right? You have long keys, but you only manage small number of students. So the question, do you want to use an array to store these students' information with index? Because here index quite long. Think about that. All right? Yeah. So you cannot use keys as indexes directly. Indexes for an array directly. Okay? Yeah. Think about it. Suppose if you use an index to store, let me draw this line segment as the array. It's quite long. Yeah. Because you need to use the student number as the index. That's how many digits? I think, look at that. 8, 7, all right, 7 or 8 digits, right? That long. So you need so many large number of memory locations, but you only store 40 students, right? You request large amount of storage space from memory, multi-billion, yeah, that huge amount of space, but you only use 40 of them. 40 of them, yeah, because you only have 40 students. So that's not efficient. Right? So that's the reason nobody used this method in the real world. Okay? Yeah. All right. Now, but I said we use this bad one. Yeah, it's a bad one. But we do not throw it in the trash immediately. But because we want to use a nice property of it, big of one, search performance. That's the part we need. Okay? So we want to preserve this property. Okay? We don't want to throw this property away. We keep it. But the bad part, long key management, that's the bad part. Can we improve it? Can we do some special work on the long keys so that we don't need huge amount of memory? We only need amount of memory that's just enough to hold all your data items. That's the idea. Just enough to hold all your data items. Right? Yeah. So that's the, so here, try to learn from this kind of thinking. Because in the real world, when you need to solve real world problems, you may have the situations like this. You have to start from something not very good, but there are some useful properties. So you still want to keep those good properties. Here, this property we want to keep. But we improve the bad part. Long key management. The bad part. All right, so next question. How to improve the efficient way to manage long search keys. In other words, how to make long search keys shorter. Shorter. If we have, think about it, suppose if it's possible, we can find some magic way to shorten the long keys. How about that? To make it shorter. And then we use the index search, but this time with shorter keys, can we do much better? Okay? That idea, pretty simple, right? Pretty simple. Yeah. So the question, how to make the long keys shorter? Truncation, is it possible to do truncation? Truncation, sort of, okay, sort of. Truncation, definitely truncation can make the long keys shorter. Yeah. But good or not, another question. It may not be good. Okay? Direct truncation may not be good, right? Yeah. Direct truncation, because two different keys, when you do truncation, for example, last two digits, two different keys may have the same last two digits, right? So truncation, direct truncation may not be good. Yeah, because two different keys after you do truncations, you get the same key. That's really bad. Okay? But can you fix it? Fix that problem? Yeah. Direct truncation not good. Can you do indirect truncation? Can you do some, sophisticated truncation? Right? Think about that. Sophisticated truncation. Okay? All right? That's the hashing idea. Hashing. Okay? Hashing way to do truncation. Okay? Yeah. All right. So let's see the details. How to make keys shorter. How to map keys to slots. If we can make long keys shorter, then we have a chance to map those keys to limited small number of slots to store our data items. All right. Mapping strategy. So here you will see the magic occurs in the mapping. You have freedom to choose mapping, right? Here, the mapping algorithm, that's the freedom you have. You have a lot of freedom to choose your mapping strategy. A good mapping strategy, you will get very good key shorten method. Okay? Key shorten method. make your key very short, but not many collisions. Many different keys. If you do some shortened algorithm, you map them to the same slot. That's a bad. Same slot. That's collision. Too much collision. That means your algorithm is bad. Algorithm is bad. If your mapping results in a lot of collision problems, your mapping is bad. If your mapping would not result in too much, very little collision, that is good. That's good. Good mapping. So let's look at this problem. What is a good mapping? Fast calculation. Your mapping, you need to do computation. Hey, when you do mapping, you need to do computation. Okay? But that computation should be very fast. Otherwise, it does not make sense. You waste too much time. Your goal is for faster search, but you spend too much time doing mapping, it will be slow. So it must be fast calculation. Evenly distributed among all the slots. Mapping, after you apply certain mapping strategy, so you get a result, key numbers, keys, but that usually those keys would give you locations of the slots. Locations of the slots. But you like to have those locations evenly distributed among all the slots. That's the ideal case. Not concentrated, small region, that's bad. But spread out, evenly distributed. All right. Not sensitive to any pattern. Another requirement, sensitive to any pattern. Because the given keys, they could follow certain pattern, special patterns. You don't want to design some mapping algorithm. For some of the patterns, it performs well, evenly distributed. But for some of the special patterns, very bad. Okay? Data map it to small region as a cluster. That's really bad. Okay? So you want to make your mapping strategy not as sensitive to any pattern. That's good. That's the ideal case. Okay? No matter what pattern it is. Okay? You always do well. So your mapping strategy always performs well. Okay? So you can see these three requirements. The first one, relatively easy. Okay? So we try to avoid complicated calculation. But the second and the third, not easy. Not easy. All right. Yeah, so implementation. Now let's look at a few implementation methods. All right. Choose appropriate math functions. The mapping strategy, basically, you just choose some math functions. That's all you need. Because you have the keys. If you have some math functions, can you plug in those keys? Because the functions will return some values. Okay? So here you can see, now the problem becomes how to design some appropriate math functions to do the math. All right. Yeah. Hash functions. this kind of special functions, we call them hash functions. So next we will study some popular hash functions. C.2 hash functions, division method. The first method, division method. We want a simple, good or not, we try to improve. First, we have some simple methods. If it's not good, we try to improve it. Keep improving that method. All right? Yeah. Hash function design, division method, because this is the simplest one. So let's start from division method first. Assume that all keys are natural numbers for simplicity. Later, we remove this requirement. For our initial understanding, we make this assumption. Later, for any strings, we can use as keys, right? Because given a string, we can convert to numbers easily. We can convert to numbers easily. So we don't worry about how to handle string keys. Non-natural number keys can be converted to natural numbers easily. So we don't need to, spend much time on it. There are n slots. Assume our data items we need to store n slots in memory. How to map a relatively large key k to one of the slots. Yes. Hash function design. That's our hash function design. Okay? All right. First method, the simplest method, do this modular operation. Hash function h of k equals k mod n. That's simple. All right? Yep. Mapping to n slots. But it may not be good. This way is simple, but it may not be good. It may not be good. But that's our first step. We get a simple hash function. Easy to calculate very fast. Yep. To do calculation very fast. Question, evenly distributed? Definitely not. Okay? Definitely not. It depends on keys. Keys with different patterns. Different patterns. For some patterns, you have a lot of clusters. Unused space also in your hash table. Tables, we call it hash table. Okay? All right. Called by any pattern, yes, we will see. I will give you some examples. So you will see. It's very easy to find some pattern to beat this pattern. All right? Make hash function robust. How to make hash function robust? We want to improve it. Make it robust, not sensitive. All right. In the division method with m slots, let's look at our first example. The n, we want to look at this number because mod n, right? Our previous hash function, we mod n. So this n is important here. Let's think about n equals 15 in our first example. N equals 15. Let's take a look. What problems we may have if we use n equals 15. All right. K mod 15. Yeah, you need to do this operation. K mod 15. But we know 15 is multiple of 3, okay? 3 times 5, 15. 3 times 5. Now the pattern. So we create testing data with pattern K is a multiple of 3. That's the pattern. Now P happen to be multiple of 3. If we use this pattern to test this hash function, h of k is also multiple of 3. Yeah, because multiple of 3 mod 15 also multiple of 3, right? Also multiple of 3. Yeah. H of k, if it is also multiple of 3, because h of k, that's the remainder part, right? Because when you mod, you remove the multiple of 15, you only keep the remainder part, right? You only keep the remainder part. Then the difference between remainder and the original key k, it must be multiple of 15. Okay, multiple of 15. Then h of k equals 15 minus k, but a k is multiple of 3. 3k1, let's say. 3k1. Okay? 15 minus 3k1, you can factor 3 out, right? So the hash key must be a multiple of 3. If that happens, then only 1/3 of the slots are used. Only those locations that are multiple of 3 can be used, corresponding to the hash function values. Yeah. So 2/3 space wasted, right? Because you only use 1/3 of the space. 2/3 of the space is wasted. That's not efficient. That's a bad hash function. The reason you know n is multiple of some number. Multiple of any number, you will get this. Multiple of any number, you will get this kind of problem. Okay? How to avoid this? Based on this example, can you make some suggestion to avoid things like this happen? Harris?
No.
How to avoid multiple of some number? Right? The question. We want to avoid to choose n to be a multiple of any number. Is it possible you can find such special n that are not multiple of any number? Is it possible? Among all the integers, are there some numbers that are not multiple of primes? Prime numbers. How about prime numbers? Right? Prime numbers only multiple of 1 and itself. Other than 1 and itself, no other factors. No other factors. So you can see primes, good choice. For this method, we like to take prime numbers for n. Okay? Right. Make hash function robust, number 2. In the division method with n slots, method number 2. N equals 2 to the rth power, power of r. Okay? 2 to the power of in this situation, look at the k mod 2 to the r. Especially when you consider the binary representation. Binary representation. If you mod 2 to the r, basically you just truncate the bits, right? You truncate certain number of bits. Higher position bits. Only keep the last r bits. Remainder, that's the remainder bits. If you choose this r. Then you can see the problem. It's very easy to beat this method with the pattern. If two keys have the same last r bits, if the pattern given in this way, then the performance is very bad because you will have a lot of collisions. A lot of collisions. So that's another example that can make your algorithm perform poor. Yeah. All right. Then, savings swap. So a good choice for division method. Based on those two examples. Now we feel if we have freedom to choose our hash function, we want to avoid those simple things. A prime number that is not too close to any power of 2. Okay? If close to power of 2, still not very good. So a prime number that is not close to power of 2. Now, that should help us to beat most of the patterns. Most of the patterns. Okay? Yeah. All right. Yeah. It is expected to be robust against any pattern. So for the division method, that's the best thing we can do. Okay? The best we can do. But you you cannot expect this algorithm can solve all the problems. The general performance, not too bad, but still some problems. Some problems. All right? Okay? It's empirical. You can do experiments. You can do experiments. So it's hard to do rigorous analysis. So we say it's empirical. Good or not, we need to do a lot of experiments. Okay? All right. It cannot be proved, rigorously, right? It is possible to create a special pattern to make it perform poor. Actually, any hash function, there is some special pattern that can defeat that. But if the probability is very slow, so we don't worry. Okay? If the probability to break that hash function very, very small, so that wouldn't work. Okay? All right. C.3, another. So this one, multiplication. This one, it should be better than division. So we have more freedom. Division method, we do not have too much freedom. Okay? Prime number, close to power of 2. We do not have many choices. But for multiplication method, then we have a lot of freedom to choose when we design hash function. And we have more confidence to make it robust against most of the patterns. So let's look at this interesting idea, division method. All right. Hash function design, this time, multiplication method. Okay. Choose a constant A in the range P, because that's a math function. Basically, we want to find a special math function. Okay. Yeah. So here, choose a constant A in the range. We need to control the range. There are n slots. We need to control mapping range corresponding to those n slots. So this A, we choose a real number between 0 and 1. Because if A is in this range, A is constant in this range, we can control it, right? Think about it. So if we have an A in this range, then we do multiplication with A, so we can change the mapping hash function values to many different places. All right, look at this hash function. K times A, K integer, it's not integer. Integer times A, okay? Yeah. Do multiplication. After this multiplication, you have some integer part, but you also have some fractional part. The integer part, after you mod 1, integer part is gone. You throw away the integer part in the multiplication and K times A, Ka. You only keep the fractional part. Okay? The fractional part, then you multiply n. Because you want to scale it to n slots. Your final locations, you have n slots. So you scale the number covering n slot location numbers. But that multiplication, that product, usually it's not an integer. So you take the floor function to make it integer. That's your slot number. That's a hash function number. In this way, you want to get a robust hash function. Think about it. Think about it. Yeah. Because this way, choose constant A. How to choose A? You have a lot of freedom. So many different A's you can choose in this range. A lot of freedom. Okay? All right, so you want to think about for what A you can get good hash function, robust hash function. For example, is 1/2 a good one? A equals 1/2. Is a good one? Not good, right? Because all even numbers, if you multiply by 1/2, that's integers. You mod 1, integer all gone, you only have 0. So all even numbers would be mapped to 0. That's really bad. Very bad. So you want to avoid. You don't want to take numbers like 1/2. How about 1/4? Still not good, right? 1/4. All integers with multiple of 4 all mapped to integers. Up, then you do mod 1 all gone, have 0 left. 0 times n also 0. All mapped to 0. So that's not good. Okay? Can you imagine any special number when you do multiplication with integer multiplication with a? You always have fractional part. Okay. 1 by 3. 1 by 3. How about if I do multiplication k a multiple of 3? How about that? If k multiple of 3, 1/3 integer, right? So it cannot be 1 over any integer, right? 1 over any integer. Or it cannot be any fraction like this, right? P over Q. Because you can multiply Q multiples. K equals Q multiples. Then you get integer. Okay? Yeah. How to choose special A's so that you multiply any integer, you always get fraction.
Irrational number.
Great, irrational number. Irrational number would make you get that. Okay? Irrational number. Let's review a little bit. Irrational. What are irrational numbers? Can you give me the definition of irrational numbers? Oh, first, can you give me one irrational number? So let us see.
Square root 2.
Correct. The most famous irrational number. Square root of 2. So pi, right? Pi. Okay. E. Okay. Many. Do you know among all the real numbers? So here we only consider real numbers between 1, 0, and 1. If we look at the numbers, we put them into different categories. Only 2 categories, right? Rational and irrational. Right? So if we use these 2 categories, first one rational, second irrational. Right? Which one, which type? We have more numbers.
Irrational.
Irrational. Irrational. We have more irrationals than rationals. How do you see it? How do you see we have more irrationals than rationals?
I know an irrational number goes on forever and it has no pattern. And there just happens to be a lot more of those than numbers with patterns.
Actually, it's not easy to show irrational numbers more than rational. Not easy to show, but one way to see it. Look at all those numbers, they occupy the space between 0 and 1, right? All those numbers, they spread in a dense way, dense. There is no room. You cannot find a gap, right? All those numbers spread between 0 and 1, there is no gap, right? So we say they are dense. They spread, distributed in a dense way. No gap. Can you find a gap? The gap means there is no number there. Okay? There is no gap. All So they occupy the space. What is the length of the total space? The length is 1. Between 0 and 1, the length is 1. So dense, all right? Yeah. Then, if you calculate the space occupied by the rational numbers and the irrational numbers, now you can look at the space occupied by the rational numbers, irrational. Within space 1, how much occupied? Yeah, so the total space is 1, occupied by the rational numbers and the irrational numbers. Yeah. Different type of number, they occupy different space, right? So you will see rational numbers, the space occupied by the rational numbers, 0. Irrational 1. That huge difference. Comparing to irrational numbers, the space occupied by rational 0. Very sparse. Okay? So the irrational numbers spread very sparse. Okay? Almost, other than the sparse rational numbers, almost all the numbers are irrational. That huge difference. How to imagine, right? Yeah. If I ask you how to imagine it, it's hard to imagine. Yeah, because we know we cannot see it. How to imagine? But let me point out one thing, another property that's interesting. Okay. Irrational numbers are countable. You can count. Countable. Countable. Do you know the meaning countable? Mathematically, not in English. English, you know, countable, right? Yeah. Mathematically, how to make a group of projects, a group of objects countable. Countable. Count. So you use natural number, you count. 1, 2, 3, 4. Yeah. Countable means you can create a one-to-one mapping to these numbers. The first number corresponds to 1, second 2, 3. You can make one-to-one correspondence, okay, to cover all the objects you want to count. That's countable. Okay? Rational numbers, you can make it correspond to 1, 2, 3, all countable. To cover all, right? Countable. Because rational numbers you can represent as P over Q. P integer Q. All rational numbers can be represented. P over Q. Numerator, denominator. So then people can design a strategy to, to assign a number to it. The first number, second number, to count it. P over Q, to cover all P of Q using natural numbers. Okay? That means countable. But irrational number is uncountable. Uncountable. You cannot. Uncountable. You cannot. So if you use 1, 2, 3, you cannot cover all of them, right? You cannot. You cannot cover all of them. Uncountable. Yeah. So that means uncountable is more than countable. Okay? Countable, you can count, right? Uncountable, nobody can count them. Too many, right? Too many, so you cannot count them. Uncountable. Okay? Yeah. So the irrational numbers, uncountable. Right. So here, we choose A, some irrational number. All right, so fractional. A good selection of A that can break most of the patterns, it should be an irrational number. Yeah. So I hope after our short discussion, so you get to know about irrational numbers. You can see, it's useful, it's very useful. Here we need an irrational number. Okay? Yeah. Go golden ratio is another irrational number. Golden ratio, you can use it. But golden ratio is out of the range, right? Not in the range between 0 and 1. So you need to change a little bit. Or you minus 1, you put it in the range, right? Okay. Subtract it by 1, because you have integer part, throw it away. Minus 1. So use phi minus 1. A equals phi minus 1. So you can design your hash function. A perfect hash function. Yeah. Before we finish this topic, let me describe a perfect hash function. Yeah, actually, the 3 requirements we saw before already, the perfect hash function. What is a perfect hash function? Always map 2 keys to 2 different slots. No collision. That's the best we want to have. Right? The perfect hash function. Always map 2 keys to 2 different slots. But there is no perfect hash function. No hash function. Perfect. Nobody can get a perfect hash function. Okay? Sooner or later, you will map 2 different keys to the same slot. But don't worry, even if that happens, we can resolve it by some other strategies. But we want to make that percentage as small as possible. The case, so we call it collision. Collision case, we want the probability as small as possible. If the probability is high, then your performance would be poor. If the probability is small, your performance will be better. Collision problem. The collision problem, 2 keys are hashed to the same slot. Nobody can avoid it. We need to deal with it. Right? But we want to control the cost. If the collision occurs with very small probability, then our overall performance will be good. Our overall hashing technique we use for search operation will be very good. Okay? All right. Yeah. Our next topic, we will talk about collision resolving strategies. I'll just give you a few commonly used collision resolving strategies. Then we will finish the whole hashing. Okay? All right. Yeah. So then next week you will have the Thanksgiving break. I will assign you homework assignment number 2 soon. Yeah, soon. So then you will turn in after Thanksgiving break. Okay? So I plan to give you 2 weeks, including Thanksgiving break and another week. So total 2 weeks. Homework assignment number 2. All right, that's it.